In this video, we're going to continue our discussion of hypothesis testing. We're going to be testing the claims about proportions in the first video, and in the following video, we'll be testing claims about means. The two methods that we're going to use to test these hypothesis claims are the p-value method and the critical value method. We discussed the basics of those in the previous video, but now we're going to do some more thorough examples. Okay. When we're assessing these test statistics, we need to have the formula for our test statistic for a proportion. So remember, a couple of videos ago, our test statistic that we talked about was p hat, which is the sample proportion, minus p, which is the population proportion, divided by the square root of the population proportion times its complement, divided by how many items in our sample. We need this test statistic for both methods, for the test statistic critical value method, and for the p-value method. For the p-value method, we obviously need the p-value, and remember the p-value is the probability of getting a test statistic that is at least as extreme as our test statistic. It is the area to the right in this case, because it's a right-tailed test here that we're looking at. It's the area to the right of our test statistic from our data. If this is a two-tailed test, it could also be the probability then in both tails, where you would take the probability in one tail and multiply it by 2. Okay, let's start with the p-value method. So, for an example, among 726 babies born to couples using the XSORT gender selection method, 402 of them were girls. Use these results with a 0.05 significance level to test the claim that a proportion of girls born to couples using this method is greater than 50%. Okay, first step. Write these steps down. These steps are going to be the same for all of the problems that we're going to do. First step, identify the claim. The claim is that the proportion of girls born to couples using this method is greater than 50%. So P is greater than 50%, or 0.5. Second thing we want to do is identify the opposite of the claim. So the opposite of P is greater than 0.5 is P is less than or equal to 0.5. Now, using those two claims, we're going to identify the null hypothesis, H0, and the alternative hypothesis, H1, and correspond those to the claim. So the null hypothesis, it's always the claim with the equals to sign in it. There's two ways that you could write the null hypothesis here. The most basic way is just to write the null hypothesis as P equals 0.5. But some textbooks, you might also see that P is less than or equal to 0.5, just like we have in step 2. Both would be okay for the null hypothesis. The alternative hypothesis would be the inequality statement the one that doesn't have the equals to. So H1 is P is greater than 0.5. And since it's greater than, it's a right-tailed test. Okay, step 4. Calculate the test statistic. So here's where we're going to use our data. Since we're talking about proportions, we're going to use the Z test statistic here. So P hat, remember, is our sample proportion, 402 divided by 726, minus P, which is the population proportion, so that's 50%, divided by the square root of P times its complement over the total number of babies born, 726. So when we plug all that in and calculate it, we have a z-value, test statistic z-value of 2.89. Okay, next step. Calculate the p-value, because that's the method that we're going to use, of this test statistic. So since this is a right-tailed test, P was greater than 0.5, we're going to find the area to the right of our test statistic. If it were a left-tailed test, we'd find the area to the left of the test statistic. And if it were a two-tailed test, we'd find the area to the right or the area to the left depending on whether the test statistic is positive or negative, and multiply by 2. In this case, since we're finding the area to the right of our test statistic is 0.9981. I'm sorry, the area to the left of our test statistic is 0.9981 from our standard normal distribution chart, our z-scores. So the area to the right will be 1 minus that. 1 minus 0.9981 is 0.0019. Okay, here's where we make our decision. In the p-value method, we compare the p-value to the significance level. So in this one, since our p-value is only 0.0019, and that is smaller than 0.05, we're in the critical region. We are going to reject the null hypothesis. Okay, let's interpret these results. Now, in order to interpret these results, I want to go back to the previous slide. So remember, we are rejecting the null hypothesis because the p-value is too low. When we reject the null hypothesis, we're going to cross that out. That means that it supports the claim that p is greater than 0.5. It supports the alternative hypothesis because we rejected the null hypothesis. So if we're going to support the claim that p is greater than 0.5, then we would say, yes, there appears to be enough evidence to support the claim that the proportion of girls using this XSORT method is greater than 50%. Okay, let's do another example. Of 745 randomly selected adults, 589 said it is morally wrong to not report all income on tax returns. Use a 0.01 significance level to test the claim that 75% of adults say that it is morally wrong to not report all the income. Okay, just like in the last problem, step 1, identify the claim. The claim is that 75% of all adults say it is morally wrong to not report the income. So P equals 0.75. Then we'll identify the opposite of that. So the opposite of that would be P is not equal to 0.75. Okay, so we have our alternative and null hypothesis to identify here. Remember, the null hypothesis is the one with the equality, so that would be P equals 0.75. And the alternative hypothesis would be the one with the inequality. P is not equal to 0.75. Since this one doesn't have a greater than or less than sign, it's a not equals to, it's a two-tailed test. Okay. In both of our methods, we're going to always have to calculate the test statistic. So calculating the test statistic here, again, since we're dealing with proportions, we're going to use the Z test statistic. And remember that P hat is our P hat is our sample proportion, P is our population proportion. So 589 out of 745 comes from our sample, and the P, the 0.75, is from our proportion. So when we plug all these in, we get a Z value of 2.56. Okay. Now we need to figure out the P value that corresponds to that test statistic. Since this is a two-tailed test and we got a positive test statistic, we'll find the area to the right of that. So the area to the right of our test statistic was 0.9941 minus 0.9948, which is 0.0052. And when we double that, we get 0.0104. Now remember, we're comparing the p-value to the significance level. So since our p-value is not smaller than the significance level, then we're not in the critical region. We fail to reject the null hypothesis. So I'll say it one more time. Since our p-value is bigger than the significance level, we are not in the critical region and we fail to reject the null hypothesis. So let's interpret that. And again, I want to go back to the previous slide. If we fail to reject the null hypothesis, that means that will reject the alternative hypothesis. So the claim of the null hypothesis, p being equal to 0.75, is supported. In other words, there does appear to be enough evidence to support the claim that 75% of adults say it is morally wrong to not report all of the income. Okay, let's talk about the critical value method. For the critical value method, we're going to have a lot of the same steps. So for example, let's say players make 839 challenges in the first US Open, and 257 of those challenges were successful. Use a 0.01 significance level to test the claim of that the proportion of challenges that are successful is less than 1/3. Okay, so our claim, the proportion of challenges that are successful is less than 1/3. And we'll round that to 0.33. So our proportion is less than 1/3. The opposite of that would be the proportion is greater than or equal to 0.33. So for the null hypothesis, we would have p is either equal to 0.33, or we could use p is greater than or equal to 0.33. As long as it has an equality, it's fine. And the alternative hypothesis would be p is less than 0.33. In this example, since it's p is less than, now we're going to have a left-tailed test. Okay, let's calculate the test statistic because we always are going to need to do that. Again, we're still dealing with proportions, so we'll use the Z test statistic formula. And our population proportion is 0.33. P hat, our sample proportion, is 257 divided by 839. And we plug that in, we get a Z value of negative 1.46. Okay, so next step. Identify the critical value that corresponds to a 0.01 significance level. So this is what we've been practicing for a while. If we look up on our standard normal distribution chart or use our graphing calculators to find the critical value that goes with alpha, 0.01, we should get negative 2.33. But remember that the test statistic was only negative 1.46. So at negative 1.46, we are not in the critical region. Since if the test statistic did fall in the critical region, we reject the null hypothesis. But our test statistic, negative 1.46, is not in the critical region. It's bigger. So it's not more extreme than our critical value, so it does not fall in the critical region. That means that we fail to reject the null hypothesis. We are not in the critical region. Okay, let's interpret that. If we fail to reject the null hypothesis, then we can support the null hypothesis of H naught being P is equal to 0.33. Or greater than or equal to 0.33. That means that we do not have enough evidence to support the claim that challenges are successful less than 1/3 of the time. That was the original claim. Okay, one last example. In a study of 420,095 cell phone users, 135 subjects developed cancer of the brain or nervous system. There is a 0.034% cancer rate of non-cell phone users. Test the claim that the cancer rate of cell phone users is different from that of non-cell phone users. Use a 0.005 significance level. Okay, and again, we're going to use the critical value method here. So to identify the claim, it's just that the cancer rate of cell phone users is different from non-cell phone users, so that P is not equal to the 0.00034. The opposite would be that P is equal to the cancer rate of non-cell phone users, so P equals 0.00034. That one will be the null hypothesis with the equality, and the not equals to one will be the alternative hypothesis, giving us a two-tailed test. Always need to find the test statistic. Again, since we're talking about proportions, we're going to use the Z test statistic here. Plugging in our sample proportion, we have 135 out of 420,095, and the population proportion is 0.00034. So we plug that in, we get a Z test statistic of negative 0.66. Okay, we need to compare the test statistic to the significant level's critical value. So the next thing we need to do is figure out the critical value for the significance level. Now remember, the significance level is 0.005, but we have to split this into two tails. So when we divide it into two tails, alpha over 2 in each of them, we get 0.0025. The critical values that go with those 0.0025 areas are 2.81 and negative 2.81 for Z. But our test statistic is between those two values. So it's not more extreme than the two critical values. So the number we get from the data, the test statistic, is in the white region in the middle and not in our critical region. That means that we fail to reject the null hypothesis. Okay, so when we fail to reject the null hypothesis, let's go back to that and interpret it. That means that we are rejecting the alternative hypothesis, so the null hypothesis could be true. The proportion could be equal to 0.00034. However, the claim was that it was different from. So our interpretation is there does not appear to be enough evidence to support the claim that the cancer rate of cell phone users is different from that of